Okay, today we're going to go over sigma bonds, pi bonds, and bond strength. All right. So let's do sigma. Sigmas are actually pretty simple. Sigma is a Greek letter, and it looks like an O. It kind of looks like a cursive O. It looks like this. That's the signal for sigma. And you all know what pi is. You should from elementary school math, 3.14. That's the Greek letter pi. Now, we're going to do sigma bonds first. Sigma bonds occur in single bonds in which the electron clouds overlap. They overlap each other. Basically, their valence shells overlap. If I had a molecule like hydrogen gas, H2, here's the nucleus of hydrogen, there's the electron cloud. And then you have another hydrogen atom, here's H and here's H. And guys, they're bonded together. If I drew the dot structure, it looks like an H with just a line between them, that's a bond. Well, as you can see, their electron clouds are overlapping each other. So right in here, this area right here, that overlap that I just shaded in, that would be the sigma bond. Remember, sigma looks like the letter O with the kind of little swirly at the top. So wherever two valence electron shells overlap each other, that's going to be a single bond. And I have a little cheat sheet for you. One single bond equals one sigma bond. A double bond is one sigma and one pi bond. And then a triple bond is one sigma and two pi bonds. I know I haven't gone over pi bonds yet. We'll get there, but that's your little cheat sheet. That's actually going to make it very simple for you. So let's just do a quick example. All that you need to know a sigma bond is when two atoms that are forming a bond overlap. That's it. So let's just look at an example. Let's say I have water. How many sigma bonds are in water? Arshan? Two. You have one here. You have one here. 1, 2. Max, how about methane? CH4. How many sigma bonds are here? 4. That's right. 1, 2, 3, 4. Very good. How about, let's see, what am I thinking? Ooh, propane. Y'all just did propane. Carson Cheeseman. How many sigma bonds are there in propane? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. No, there's more than that. 9, 10. There you go. Good save. So whenever you see a single bond, that is a sigma bond. Let's do a couple more. How about ammonia? NH3. Oops. Let me redraw that. How many sigma bonds are in NH3? Ammonia. 1, 2, 3. Here's another question I have for you all. Listen up. This is going to help you win tomorrow. Why is this correct? And why is this incorrect? What do you think? Yeah, Jude.
Because all of the atoms aren't equally spaced apart.
From what? What are they trying to get away from?
Each other. Or they're trying to get away from
that guy.
Oh, so they're trying to
unshared pairs.
This unshared pair is creating a huge electrostatic repulsive force. And what it's basically doing is it is forcing the other bonds down. To be clear, and I don't think I've been clear enough on this, let me ask you all, what creates a greater repulsive force? Electrons that are in a bond or electrons that are not in a bond? Not. Remember, think of the ones that are not in a bond as being jealous. So they're resentful and they hate everything. The ones that are not in a bond, up here, these two, they are creating a tremendous repulsive force, which is pushing all the other ones that are in a bond down. Yeah.
So the bonds are trying to get away from the unshared electrons.
And they're trying to get away from the unshared electrons and from each other. As they're getting pushed down by the unshared pair because their repulsive force is greater. Okay. All right. So, are there any questions with identifying sigma bonds? That's usually pretty simple. Let's go over to pi bonds. So remember that when you have a double bond, it results in 1 sigma and 1 pi. And when you have a triple bond, you have 1 sigma and 2 pi bonds. A pi bond forms when parallel orbitals overlap and share electrons. We'll do a few examples for you guys to just identify how many pi bonds there are. Should be pretty straightforward. The shared electron, the shared electron clouds of a pi bond occupies the space above and below the line that represents where they are bonded together. Okay, so that's just a lot of words. You guys said the definition, but let me actually give you some visuals here to help you out. Okay, ethene, C2H4. It looks like this. So that's just the dot structure. That's something that you can do in class tomorrow. That's if I were to ask you guys, I want you to draw the molecule ethene, C2H4. That is what I would be hopeful that you all could come up with. So here's how this looks when we're talking about pi bonds and sigma bonds, okay? Here's a carbon. Here's a hydrogen. Here's a hydrogen. Here's a carbon. Here's a hydrogen. Here's a hydrogen, okay? I have no bonds drawn yet. So just focus in on that. You ready? There's the orbitals for the hydrogens. There's one of the orbitals for the carbon. So by definition, when one orbital overlaps, an orbital of one atom overlaps the orbital of another, what type of bond is that? Sigma or a pi? That's a sigma, exactly, good. That's a sigma bond. How about here? What is that? Very good. How about here? Very good. And how about here? Very good. Okay, great. Now, what about on the other side here? We got this, and we got that. No, that's still sigma. That's still a sigma bond. They're overlapping each other. Let me be clear. I'm going to shade this in. Check this out, guys. Here, is that an overlap? That's not a good color for you to see. Can you see that? That's an overlap. How about here? Is that an overlap? Yep. How about here? Overlap. Here, overlap. And then right here, that's an overlap. So that is a sigma 2. Wherever you see overlap, that is going to be sigma bonds. But now, you're going to see these here. This is because of the double bond. These are basically going to overlap each other. And this is going to be a pi bond. And a pi bond has 2 lobes. So this is all one pi bond. There's no electrons that you see. I know that I just heard some of you go, wait, what? This is just the, these are formed from the double bonds that are between 2 neighboring atoms. So the fact that you look over here and there's a double bond right there, well, as I gave you your cheat sheet, a double bond is 1 sigma, 1 pi bond. The sigma is just because they're overlapping. But also, the forces that are going to be formed due to the double bond are going to be the pi bonds. And so whenever you see a double bond, there's just 1 pi. And whenever you see a triple bond, there's 2 pi. Yes, Arshawn?
So between the carbon, the sigma is 1 pair of electrons, and then the pi is...
The pi bond has 2 lobes. It's considered 1. So this is 1 lobe. This is the other lobe. 2 lobes is going to result in 1 pi bond.
Are the lobes like electrons?
The lobes are going to be the repulsive forces of the electrons that they can generate. Yeah.
So how does each carbon atom now have like 5 orbitals?
It's not an orbital. That's where I think the disconnect is. It's not an orbital. It's just the force that's generated by the double bond. It's already there. It's not an extra orbital on either side.
So if the electrons are next to each other, how does that form a bond?
Because the double bonds have a greater strength. And so that strength is going to be amplified above and below. And that force can overlap.
Like forcing it in so it's stronger?
Yeah. Because double bonds are stronger, and so they're able to have more repulsive energy. And there's repulsive energy on top and on the bottom, and they don't necessarily overlap, but they're going to parallel where that double bond is, right there.
So it's like repelling the sigma bond.
Yes.
So is a triple bond even stronger than that?
Yes. A triple bond is even stronger than a double bond. All right. In fact, I have a great way to hopefully demonstrate this for you all next. And so let's get to bond strength. Okay, I'm glad that I only have one chem classes here because when I would have 6 chem classes, I would go through a lot of pencils. I want you to watch this. Let's say that I have hydrogen bonded to hydrogen. That's a single bond. Here's oxygen bonded to oxygen. That's a double bond. And here's nitrogen bonded to nitrogen. That's a triple bond. So remember, this is H2, this is O2, and this is N2. So I want you guys to check this out. Here's a pencil. This pencil represents a single bond. See, it's a very long pencil. Now it's a 2. These 2 pencils represent a double bond. What is longer, a single bond or a double bond? Yeah, this was, before I broke it, here's a single bond. And then, here's 2 doubles. I didn't break the pencil evenly, that's my fault. And now, ready? It's not the easiest thing to do. This is a triple bond. Now, who thinks they're strong enough to break those in half? Why not? They're so short. They're shorter than this. This is easier to break because it's longer and there's only 1. This is harder to break because there's 3 of them and they're really short. So generally what we deal with bonding is that single bonds are the longest and the weakest. Triple bonds are the shortest and the strongest. It's like trying to break a pencil in half. 1 pencil is easy. 2 pencils, you have to put a little more strength. I had to put a little extra oomph into that. 3 pencil bits, they're really short. I can't break those. They're too short. And we'll just put intermediate for the oxygen. The oxygen is going to be, the double bond is going to be shorter than the single, longer than the triple. It's going to be stronger than the single, weaker than the triple. Yes, Carson?
I'm confused why the nitrogen is a triple bond.
If you have nitrogen here, how many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. You have another nitrogen. 1, 2, 3, 4, 5. How many valence does that nitrogen have now? How about the other one? What electrons are they sharing? The 3 in the middle from each one. So that forms a triple bond. That's the only way that you could get 2 atoms with 5 valence electrons each to complete each other. If you try to do a single bond or a double bond, you would not be able to make it so that each of them has 8. They would be short.
How do you know which way to write it?
That's where the practice comes in. That's what we're going to be doing tomorrow. I totally get how you feel. I used to feel the same way. How are you supposed to know to do that? Well, it takes practice and it takes a lot of problem solving. This is like putting a puzzle together. If I gave you like phosphorus and 3 chlorines, and I told you, okay, you've got to figure it out, put them all together so that each of them becomes stable, it takes practice. But eventually, we're going to get it. And so that's what tomorrow after your vocab quiz is going to be all about. A lot of practice with putting these together. Carson, Dai, you had your hand up?
Yeah, can I ask a question?
Go ahead. Yeah,
Can you draw a triple bond?
I just did.
I mean, like, the diagram thing.
What do you mean a diagram?
I don't know.
Now, let me ask you all this. How many sigma bonds in a holding hydrogen molecule together? Okay. How many sigma bonds holding an oxygen molecule together? 1 sigma. How many pi bonds? Right. How many sigma bonds in a triple bond? How many pi bonds? Very good. Okay. Let's continue. We have about 10 minutes. So let's continue with bonds and energy. Okay. It takes energy to break a bond and it takes energy to build a bond. But it depends on which way energy is going. A few weeks ago, we discussed endothermic and exothermic. Endo means energy is being absorbed. Exothermic means energy is being released. If you drive and you turn off your car engine and you put your hand on the hood of the car, you feel the heat from that car. The car is releasing heat. That would be exothermic. But if you hold some ice cubes in your hand, you are obviously warmer than the ice cubes. The ice cubes are absorbing your heat. Something that is absorbing heat feels cold. Just like how something that is absorbing color is black. Something that is releasing color is white. Like if you look at the sun, that's white light. It's really bright. It has all the colors of the rainbow. If you have it shine through a prism, you get the color spectrum. So here's the rule of thumb. Energy is released when a bond forms. Based on your understanding of what released means, would this be endothermic or exothermic? That's right. This is exothermic. Energy is absorbed when a bond breaks. If it's absorbed, what is that term? Endo means going in. Remember that humans have an endoskeleton and a crab has an exoskeleton. Exo means out, endo means in. So let's see what you guys remember. There's my energy, activation energy. If this is going to be exothermic, would my products be greater than or less than where I started? Less, right. It's going to look like this. That is an exothermic reaction. You have time, you have energy. If I have an endothermic reaction, will I end with more or less energy than what I started with? I'm going to end with more energy than what I started with. That would be endothermic. Energy is being absorbed. So that we did that a few weeks ago. Just want to be sure you recall that. If you notice here, my energy level is at that level. And then when you end, it's lower. That means energy was lost. If I am here, and then I end there, that means energy was gained. That would be endo. Energy required to break covalent bonds is called the vocab term bond dissociation energy. It is always positive. Now, if you were friends with someone, if Colby was friends with Max, we would say that they are associates. They associate with each other. But if Max and Colby do not like each other, we're going to say that they are dissociates. They are not having anything to do with each other. They have disassociated. So to associate means to be with. To disassociate means to be apart. So riddle me this. The shorter the bond, the blank energy is required to break it. Is it going to be more or less? Or more and less? More. Remember this. Colby, you look like a strong kid. Do you think you would need to apply more strength to break these or break this? The three small ones, because they're so short. Even if I had one small one, that's still going to be tough. So the shorter the bonds are, the more energy you need to break them. And the opposite of that, the longer the bonds are, the less energy is required. And I didn't finish my sentence, did I? To break. And to break. All right. Let's put a quick definition on endothermic and exothermic before you guys go, because that is on your vocab quiz. I think you can put your own definition on this. Is energy absorbed or released in an endothermic reaction? That's right. The amount of energy at the end of a reaction is greater than at the beginning. Basically, energy is absorbed. If I showed you a graph like this, energy is absorbed. And then the opposite of endothermic is exothermic. The amount of energy at the end of a reaction is less than at the beginning. So in this case, energy is released. Okay, let's finish up. About coming to the end of the class. Here's the plan for tomorrow. Hey, do me a favor, guys. If you, all of you should be carrying your hand sanitizer with you, just because it's easier that way. Please be sure that you have some with you tomorrow. I will do my best to get enough kits for at least every 2 students. So be sure you have a good mask. Be sure that you practice proper sanitation and distance, all that. We're going to try our best. And I only have 5 kits, but I'm going to ask Ms. Tate, who's the AP Chem teacher, if I can borrow some of hers so that we can have enough for at least groups of 2, maybe 3. And you guys are going to be building a bunch of stuff like this after your vocab quiz, okay? So we'll do your vocab quiz right off the bat. Hopefully that'll only take 10 minutes. We'll spend the rest of the time building some molecules.